Good day, sweet world. So today we'll be talking about the Hall effect. So the Hall effect was a phenomena, sorry, that is experienced by conductors under a applied external magnetic field. So a good explainer video on the Hall effect is will be linked down in the description below. It's also shown in our overlay page. But as a quick aside, so the Hall effect is experienced when we have this one. So we have, let's say, this potential would create a current, as shown, positive to negative. Current would flow from positive to negative. So since we have this current, let's say this conductor is a semiconductor, we would have the flow of both our holes and our electrons. Your holes will be at the same direction as our conventional current, which is from positive to negative, since holes are attracted to the negative potential. Meanwhile, your electrons will move from negative to positive. So let's say we have this system, we have this conductor. The Hall effect happens when we expose this conductor into an external magnetic field. So this might be caused by magnets or something like this one. So let's say our magnetic field is ganito. It's going from negative Z to positive Z. So due to this magnetic field, we know that your magnetic field interacts with your charged particles, creating a magnetic force. So this magnetic force would push your electrons and holes to one direction. And pushing your electrons and holes in one direction would cause the production of what we call the Hall voltage or Hall electric field, since there will be an accumulation of charge carriers on one side or the other. And from there, we can get the properties of our semiconductors, like what kind of semiconductor it is and so on. So I'll be talking about your two different cases for semiconductors. You have your P-type and your N-type semiconductor more in detail. And so now let's go to our P-type semiconductor. So if we have a P-type semiconductor, since there are much more holes than electrons, we opt to only consider our holes in this scenario. Dito, holes lang yan. A hole moves in the x direction with velocity v, x. At the same time, it is also subjected to a Lorentz force in the y direction equal to F is equal to Q VH cross B. Due to this force, your holes will then curl to one side. So yung Lorentz force natin dito will go paganyan. Due to that force, it would curl the holes during movement na paganyan. Like so. This would cause the holes to accumulate on this side of the slab, creating positive charges here. Positive, 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 positive. To balance this out, negative charges will then appear on the opposite side. So kakaroon tayo ng negative charge dito. The formation of these charges, positive and negative here, would result in the formation of what we call your Hall electric field, since this is the electric field caused by the Hall effect. This denote this as E Hall. At equilibrium, your Lorentz force or the magnetic force and the force due to your Hall electric field must balance each other out. So dapat sila mag-equal to 0. 0 is equal to your Q VH cross B and your force due to electric field Q times E Hall. Yung Hall electric field strength natin dito, E Hall, makita natin this will then be equal from this notation. Q E Hall will then be equal to negative Q VH cross B. Canceling Q, we get that E Hall is equal to negative VH cross V. Using our scalar quantities, we'll see that the value of the Hall effect of this Hall effect electric field or your Hall electric field at the y direction, E Hall y would then be equal to V H X times B in the z direction. So yan yung scalar quantities yan. VHX times BZ. We can also get here the equation for the drift current density. Since we know that drift current density J is equal to PQVHX. Ito yung number or concentration of our holes times its charge times the velocity, average velocity of each of our holes. Equating this equation and this equation, we will get that. So, equate natin yung VHX. We have E Hall over BZ is E Hall Y. BZ would be equal to J over PQ. Or, putting E Hall in one side, we get, we will get E Hall Y will then be equal to J over PQ BZ. So this gives us, from your concentration of holes, the charge of the hole, the current density, and from the electric field, yung quantities na yan, we will then get yung value ng ating Hall electric field. So this expression contains macroscopic quantities which are characteristic of the material, like yung P, yung parameters of the experiment, J and B, and quantities which can be experimentally measured, E Hall. Through this relation, we can then extract properties characteristic for our semiconductor, for our experiment. Then let us introduce what we call our Hall constant, RH. RH is defined to be E Hall Y over JX BZ. And this equal to also, from here, E Hall JX BZ, lipat natin dito, is equal to 1 over PQ. The Hall constant, or our Hall coefficient, this provides a direct way to measure the concentration of charge carriers in our system. Since tong E-Hall natin, kaya natin itong ma-measure from the experiment, GX and BZ are experimental parameters, and Q is your elementary charge, we can get the number of holes in our system. From this, we can then see that knowing yung ating from here, we can deduce yung concentration of our holes in our semiconductor. We can also define, so this is important, lagyan natin ng box. We can also define our Hall mobility, mu. Mu is equal to H. Hall mobility of our holes, this will be equal to sigma RH, or our Hall constant, Hall resistance, or Hall coefficient. This Hall mobility, this is actually analogous to our mobility of our charge carriers. Parang same lang sila ng units. But they differ by a factor sigma. This is your Hall factor. And this Hall factor depends on the temperature and the charge carrier scattering. But usually, we just take this as like 1 experimentally. So from the Hall mobility, actually we can get an idea on the charge carrier mobility of our holes. So from here, from the Hall effect, can see that we have this relation. By using our Hall effect measurement, by getting E Hall, Gx, and Bz, we can get for the concentration, of our holes in our system. Now let's consider our N-type semiconductor. N-type. So for N-type semiconductor, we now have electrons moving to the opposite side. So opposite siya ng conventional current natin. We can apply the same treatment as what we did with the P-type semiconductor, but now we consider that electrons are moving again in the opposite direction. So the whole electric field will now be on the opposite direction since our electrons, pag tinamaan siya nitong magnetic field na to, B, E, this would curl towards pag ganito. Ito yung curl niya. Magkakaroon tayo ng accumulation of negative charges here, and your positive charges would accumulate in this direction. So yung electrons mo, ganito yung curl niya kasi negatively charged to, Q, negative times V cross B. So pag ganun siya. Then, you would have an electric field going from positive to negative. So, reverse na yung direction ng whole electric field natin. Applying the same analysis, we would have your E Hall is equal to negative VE, the velocity of our electron, cross B. The value of your whole electric field in the y direction will then be equal to E Hall y would be equal to Vex times Bz. And since nakita natin yung whole electric field natin dito, negative direction siya ng y, ito yung y natin, negative siya, we expect that this E Hall would actually be a negative value, less than 0. From here, we can also have the equation for our current density. Jx then be equal to negative NQ Vex, negative in direction ito. Equating both this one and this one, we can get again an expression for our whole electric field. E Hall y is equal to negative Jx and Q Bz. And your Hall constant, RH, again, RH is equal to E over JB. E Hall Jx Bz. This RH is equal to E Hall y Jx Bz. This will be actually equal to 1 over NQ, but since meron tayong negative sign, this would be negative. So RH, your whole constant or whole coefficient, will be equal to E Hall y Jx Bz is equal to negative 1 over NQ. And since Hall electric field here is negative in our convention, negative yan. Yan, negative yan. Kaya meron tayong negative sign dito kasi yung values ng N and Q natin, this is always positive, and it's the concentration of our electrons in our N-type semiconductor, and Q is yung elementary charge natin, 1.602 times 10 to the negative 19 coulombs. Negative yan. And from here, you can also get the Hall mobility for our N-type semiconductors, MHE. Similar dun sa kanina, we have sigma RH. Opposite value since positive yung values na to. So from our previous two scenarios, yung N-type and P-type natin, we saw that for P-type semiconductors, yung E-hole natin and consequently the RH or R-hole, this is positive. Meanwhile, for your N-type, your E-hole is negative, which your hole coefficient is also negative. This is actually really important to us. If we don't know the if we don't know the whether our semiconductor is N-type or P-type, we can look at the hole coefficient of our system. So if RH is greater than 0, or if the hole coefficient or hole constant is greater than 0, then we can be sure that our electron is majorly P-type. If RH is less than 0, then our semiconductor is N-type. And from there, we can get again yung ating charge carrier concentrations. So for our N-type semiconductors, we can get the number of electrons in our system. For P-type, we can get the number of holes in our system. So the Hall effect measurement is really important to us, since this allows us to, 1, figure out what kind of semiconductor we have, and 2, figure out how many charge carriers, majority charge carriers, are there in our semiconductor. And since this is important because we can get a lot of the important properties of our semiconductors from that information. So with that, I'll end the Hall effect. Thank you, and see you on the next one.